my name is Daniel Cohen, and today I'll be presenting my research titled Allowing for the Grounded Use of Temporal Difference Learning in Large Ranking Models via Substate Updates. And this work was completed while I was finishing my PhD at the University of Massachusetts Amherst. And I also understand this title is somewhat of a mouthful, so I want to work through it from the basics. So here we have the standard IR problem. We have a set of documents that we need to rank. So we pass these documents into our retrieval model, and we get back a ordered set of documents. And of course, we want to make sure that we actually train our model, so we update our model with respect to some metric. The most popular one is probably pairwise training. So here we want to maximize the distance between a relevant document and a non-relevant document. However, there are situations where we want to take into account more than just two documents. And some of these situations include fairness, diversification, personalization, multi-page search, pretty much any situation where we want to make sure that we're not just trying to find a relevant document and a non-relevant document, but perhaps an equal distribution of two different types of documents, or make sure that we're showing different topics in our rank list. And we need to be able to capture not just this play between two documents, but all the documents. And this is what we refer to as list-wise ranking and list-wise training. A very popular method for this task is reinforcement learning, and this allows us to directly learn a list-aware function by interacting with the environment. So here, our agent would be a ranking model, and we select the document. Our environment could be a fairness judge, it could be a user, it could be relevance judgments. We get back some reward that tells us how well our model performed and a new state. To really ground this in IR and ranking, I want to present a formulation that's very common in IR and it's been used in the past. So here, our state represents 4 documents we need to rank. We pass that to our retrieval model. It selects a action, the yellow document, as the best document for whatever metric we're trying to learn. So it could be fairness, diversification, or just straight up the most relevant document. At the next time step, our environment gives us back the 3 remaining documents, and we select the blue document. At the third time step, we select the red one, and here we get our rank list 1 through 4. And then to update our model, we perform policy gradient, specifically the reinforce algorithm. I know there's a little bit of confusion between reinforcement learning and reinforce. You get used to it. And the way reinforce works is it allows us to bring back how we performed at the end of the episode based off of the rankings 1 through 4 and update our model at each time step. And we can use the softmax function to assign how well we did with respect to judging each document in our state. But going away from IR and looking at alternative reinforcement learning methods, we have the reinforce method we just spoke about, and there's been recent work in making it pairwise, which makes it a little bit better for information retrieval tasks. But let's move away from policy gradient and take a look at other methods, temporal difference learning methods. And such methods include value iteration, Q-learning, Actor-Critic, and some of these are very capable. Actor-Critic has performed very well in a variety of tasks and often outperforms a lot of the other algorithms. But looking at what's being used in ranking and in information retrieval, it's only policy gradient. And that's not because temporal difference learning methods, or TD methods, aren't effective. As we just said, they're very effective. So there must be another reason why we're never using these algorithms. And that's due to the ease of use of reinforce. So the way IR models work is they take a single query and a single document and they score it, right? And then based off of the score, we can use pairwise training or list-wise training and update our model. But in reinforcement learning, we need to actually capture the entire state, so model all documents simultaneously. That's not feasible in our neural architecture without making it specific to whatever setup we're using it. We don't want to have to make a BERT that works on 900 documents, and then for another problem, make another BERT that can capture 500 documents at the same time. So what reinforce does is it says, forget about trying to make our specific models for modeling 10 documents at the same time. Let's perform a softmax operation. And the softmax operation now allows us to capture the full state information without having to model all the documents in our state simultaneously. And that's why this method is so popular. It allows us to do reinforcement learning using standard neural IR architectures. Temporal difference learning is a bit different, and I'll go into why. So for those of you not familiar with TD learning, I'll walk us through it. So here we have a single step in a reinforcement learning setup. We have our state. We pass it to our function that determines which action to take. So this could be a retrieval function saying to rank a specific document. And then we pass this to our environment, and we get our reward and a new state, so possibly the remaining documents. Going into a little bit more detail about what's going on, our retrieval model is actually trying to evaluate the state and which state to go next. So essentially, which document that leads us to the best future states. And we're trying to maximize the expected future discounted rewards. And the way we update this is through the Bellman update, and this is where temporal difference learning gets its name. We're essentially saying, let's update our current belief of how good the red state is based off of the reward we just received, and the temporal difference, the evaluation difference, our own evaluation of the red state and the blue state discounted by a single gamma. And this is still a little bit confusing, so let's take a look at the math and do a little bit of arithmetic. And what we see is we're saying, let's update our current evaluation of the state but by taking the difference between the actual reward we get and the reward we thought we'd get by taking that specific action. And this is different than the reinforced algorithm, but it also has some advantages. It's a lot more sample efficient. It has reduced variance because reinforced requires us to go to the end of an entire episode. So you have to rank all your documents before updating with the reinforced algorithm. Temporal difference learning lets us do this online, so you can directly change your model as the user clicks. You don't have to wait for the user to leave. But applying this to IR, we run into a little bit of a problem. So again, here's a state with a query and a set of documents. Let's say we choose a document to rank, then that gives us our new state, that blue state, with n-1 documents. And performing the temporal difference update, we get the same equation we saw before that we now understand. We're getting this nice little update to our belief of how good it is to go from the red state to the blue state. But this isn't how neural IR models work. Instead, these models look at a single query and a single document and score it. But that doesn't really play well with that equation on the screen. So let's take a look at how we do it in the IR world. So here we rank a document in our state, and let's say this blue one is the one that we think is the highest value. So we select that for our current time step, and the next time step we select this yellow document. And applying temporal difference learning through this lens, we get this equation. And this equation doesn't really make sense. So here's the standard temporal difference learning update, where we're saying we're going to update our belief of the state based off of the belief of some other states. What this other equation, this IR-specific equation, is trying to do is saying, let's update our belief of the state based off of the difference between our evaluation of two individual documents. And this isn't temporal difference learning per se. What are we actually doing when we do this? Yes, PyTorch or TensorFlow will perform the math and it won't give us an error, but are we actually learning what we want to learn? And that's the question we ask in this paper and what we actually address. So intuitively, you would think so, right? So on top is the standard temporal difference learning update where we get access to the entire state and our function operates on all the documents. On the lower half is that IR version, and that's what we refer to as substate temporal difference learning. We're operating on a sub-portion of the entire state. And really, our reward often matters only with respect to the document we choose. So it doesn't actually matter what other documents are in our state. Our reward, and therefore our expected future discounted reward that we're trying to model, should be the same. So there's something there that says that, yes, that amalgam we saw in the previous slide and on the lower half of this one actually makes sense. And to show this, we actually demonstrate that the way we point-wise score actually has these natural convergence properties. That means that our substate temporal difference learning will converge to a effective policy. And the way this works is that we decompose the state space to a set of basis points, and those are the documents in the state. And we perform this very naive interpolation, where we say, let's divide our state space up, and so any document will have its own neighborhood. And for any other point that's not a document, we'll just assign it to the closest document. And this is an incredibly naive interpolation, right? There's actually no interpolation. But this is valid. If you think about it, if you make sure you visit every single document possible, you'll eventually capture the full state information. You'll eventually fill up this square. And that's the key thing. By doing this and making sure you visit enough documents, well, you'll converge to within a region C around the proper temporal difference learning. And this is what we refer to as interpolated substate temporal difference learning, ISS for short. And this is great. We now theoretically have shown that this weird document to state update makes sense, but that has nothing to do with empirically showing it, right? C could be huge, and our interpolated substate temporal difference learning method could actually just be random. So we perform a case study. In this case, we use a recent temporal difference learning method, successor features. And what's interesting about this is it learns a fixed goodness vector as well as a dynamic state representation, which tries to capture the future states it'll visit, and it's discounted. And it's this dynamic representation that's learned through temporal difference learning. It gives a nice little new view of how we can use temporal difference learning for ranking and information retrieval. Since we're talking about reinforcement learning, we of course need to define a Markov decision process it operates in. We use the same one from MDP rank, which we actually described in the motivating example, and the reward is just a reciprocal rank. We look at 3 deep neural architectures, as that provides a very challenging setting for reinforcement learning agents: match pyramid, bidirectional LSTM, and the transformer kernel. And these represent the 3 paradigms: convolutional, recurrent, and transformer architectures. Since we're working with neural models, we of course use full text, so Insurance QA, Yahoo L4, which is a community question answering collection, and MS Marco Passage. For our baselines and methods and algorithms we use, we look at, of course, reinforce, but we also use the interpolated substate version of Q-learning, ISSQL, and of course our case study of interest, interpolated substate successor feature Q-learning. It's a bit of a mouthful, ISSQL for short. We also account for the supervised performance, so pairwise hinge loss. And in general, especially with deep neural architectures, supervised training provides a nice approximate upper bound of what we can hope to achieve with these reinforcement learning agents. With that said, we can now look at our results, and we see a very promising result with ISSQL, which substantially outperforms all the other methods, and especially outperforms reinforce. But what's even more interesting is by using this recent temporal difference learning algorithm, we can outperform supervised training at times. And this makes sense, right? Pairwise training is not the end-all be-all of ranking. It's actually list-wise training. And this allows us to really bring reinforcement learning methods into IR without having to rely on a algorithm from the 1990s, which is extremely effective. Reinforce is extremely effective. But this allows us to open up other doors. Examining the convergence properties, again, we see the same pattern. And something I want to highlight is reinforce doesn't converge, but this doesn't mean temporal difference learning methods are better than policy gradient. There are certain aspects that temporal difference learning does better than policy gradient, and this is just such a situation where we see it excel. Something that I, again, want to highlight is they're pretty much equal in different situations, so you should still always consider them both. So in conclusion, for situations like fairness, diversification, personalization, anything when you want to learn a list-wise function, we can now use any temporal difference learning method for these large state spaces, regardless of whether you have 10 documents or 1,000 documents. It doesn't matter, and we're no longer restricted to policy gradient, which I think is the most exciting piece of this work. Thank you so much for watching this presentation, and please feel free to ask me any questions you might have about this.